Section: Introduction. In this section, we explore how generative large language models can sometimes provide outdated information or create false facts, even when trained to align with human preferences using reinforcement learning or lighter alternatives. To tackle these issues, Retrieval-Augmented Generation (RAG) techniques combine pre-training and retrieval-based models to create a robust framework that enhances model performance. RAG allows for quick deployment of applications tailored to specific organizations and domains without needing to update model parameters, as long as relevant query-related documents are available. Many RAG methods have been developed to improve large language models (LLMs) by incorporating query-dependent retrievals. A typical RAG workflow involves several key steps: determining if retrieval is needed for a given query, efficiently obtaining relevant documents, refining the order of retrieved documents based on query relevance, organizing retrieved documents for better generation, extracting key information from organized documents for response generation, and eliminating redundancies. Implementing RAG involves decisions on how to split documents into chunks, the types of embeddings to represent these chunks, the choice of vector databases for efficient storage, and effective fine-tuning of LLMs. The variability in each processing step adds complexity and challenge. For instance, various methods can be used to retrieve relevant documents, such as query rewriting, generating pseudo-responses, or employing embedding models trained with query response pairs. Our study aims to identify the best practices for RAG through extensive experimentation. We adopt a three-step approach to find optimal RAG practices, comparing methods for each RAG step, evaluating the impact of each method on overall performance, and exploring promising method combinations for different application scenarios. By balancing performance and efficiency, we suggest strategies for deploying RAG effectively. Our contributions include thoroughly investigating existing RAG approaches, introducing a framework for evaluating RAG models, and demonstrating how multimodal retrieval techniques can enhance question-answering capabilities and speed up multimodal content generation. Previous works have focused on optimizing the RAG pipeline through query and retrieval transformations to improve the accuracy and relevance of responses generated by LLMs. Techniques like query transformation, retrieval source document enhancements, and post-processing retrieved documents have been explored to enhance generator output. Section Summary. In this section, we delve into the challenges faced by generative large language models in producing accurate information and how Retrieval-Augmented Generation (RAG) techniques offer a solution by combining pre-training and retrieval-based models. We explore the complex workflow of RAG, including query classification, retrieval, reranking, repacking, and summarization, and the impact of different methods on the effectiveness and efficiency of RAG systems. Through extensive experimentation, we aim to identify optimal RAG practices by comparing methods for each step, evaluating their performance, and suggesting strategies that balance both performance and efficiency in deploying RAG. Section: Retriever Enhancement Strategy. In this section, we will discuss the importance of chunking documents and how it affects retrieval performance. Chunking methods play a significant role in how well we can retrieve information from documents. Common chunking strategies divide documents into smaller parts, but it can be tricky to determine the best chunk size. If the chunks are too small, they may break up sentences, while large chunks could include irrelevant information. Llama Index improves chunking methods like small too big and sliding window. Sometimes, the retrieved chunks may not be relevant, and there could be a large number of them, so we need to re-rank them to filter out irrelevant documents. One common way to re-rank is by using deep language models like BERT, T5, or Llama, which can lead to better performance but require slow inference steps. Tilde focuses on efficiency by pre-computing and storing the likelihood of query terms to rank documents based on their sum. Fine-tuning within the RAG framework is crucial for optimizing both retrievers and generators. Some studies focus on fine-tuning the generator to make better use of retriever context, ensuring accurate and robust generated content. Others fine-tune the retriever to learn how to retrieve useful passages for the generator. Some holistic approaches treat RAG as a unified system, fine-tuning both retriever and generator together to improve overall performance, even though it adds complexity and integration challenges. Various surveys have extensively covered current RAG systems, discussing text generation, integration with large language models, multimodal capabilities, and AI-generated content. While these surveys offer detailed insights into existing RAG methods, choosing the right algorithm for practical use remains a challenge. Our paper concentrates on the best practices for applying RAG methods to enhance the understanding and application of RAG in large language models. Next, we will delve into the components of the RAG workflow, discussing commonly used approaches for each module and selecting default and alternative methods for our final pipeline. We will also touch on best practices in this section. The workflow and methods for each module are illustrated in a figure. Detailed experimental setups, including datasets, hyperparameters, and results, can be found in the appendix. We will then move on to query classification. Not all queries need retrieval augmentation because large language models already have strong capabilities. While RAG can improve information accuracy and reduce errors, frequent retrieval can slow down response times. Therefore, we start by classifying queries to decide if retrieval is necessary. Queries that require retrieval will go through the RAG modules, while others will be handled directly by the large language models. Retrieval is usually recommended when additional knowledge beyond the model's scope is needed. However, the need for retrieval varies depending on the task. For example, an LLM trained up to 2023 can handle a translation request without retrieval, but an introductory query on the same topic may require retrieval for relevant information. We suggest categorizing tasks based on whether they provide enough information to determine if retrieval is necessary. We classify tasks into 15 categories, with specific examples provided in a figure. Tasks that rely solely on user-provided information are labeled as sufficient and do not require retrieval, while others are labeled as insufficient and may need retrieval. We train a classifier to automate this decision-making process, and experimental details can be found in the appendix. We will explore how query classification impacts the workflow, comparing scenarios with and without classification. Section Summary. In this section, we focus on enhancing retrieval performance through document chunking and embedding methods, which significantly impact the quality of retrieved information. We optimize chunking strategies like small to big and sliding window to address challenges in determining the optimal chunk length, balancing between fragmenting sentences and including irrelevant context. Additionally, fine-tuning within the RAG framework is crucial for optimizing both retrievers and generators, with some approaches focusing on fine-tuning the generator to utilize retriever context effectively, while others fine-tune the retriever to retrieve beneficial passages for the generator. Section: Chunking Techniques. In this section, we explore advanced chunking techniques that enhance retrieval quality by organizing chunk block relationships. These techniques, such as small to big and sliding window, use small-sized blocks to match queries and return larger blocks containing both the small blocks and contextual information. By maintaining context and ensuring relevant information retrieval, these techniques prove effective. We demonstrate the effectiveness using the LLM embedder model as an embedding model with specific chunk sizes and overlap. Choosing the right embedding model is crucial for semantic matching of queries and chunk blocks. We use the flag embedding evaluation module with the .ms Marco dataset to select the appropriate open-source embedding model. After comparing different chunk skills, we choose the LLM embedder for its balance of performance and size over other options like BAAI, BGE large N. Enhancing chunk blocks with metadata like titles, keywords, and hypothetical questions can improve retrieval and help language models better understand retrieved information. We plan to delve deeper into the study of metadata inclusion in future work. Vector databases store embedding vectors with metadata, enabling efficient document retrieval through various indexing and approximate nearest neighbor methods. We evaluated several vector databases based on key criteria like index types, billion-scale vector support, hybrid search, and cloud-native capabilities. Our evaluation highlights Milvus as the most comprehensive solution among the options, meeting essential criteria and outperforming other open-source databases. The retrieval module selects the top K-relevant documents from a pre-built corpus based on query document similarity. We evaluated 3 query transformation methods using the LLM embedder as the query and document encoder, query rewriting, query decomposition, and pseudo-documents generation. Combining lexical-based search with vector search has shown significant performance enhancement. Our study on different retrieval methods on TRECDL 2019 and 2020 datasets indicates that supervised methods outperform unsupervised methods. Hybrid search with hide is recommended as the default retrieval method for its notable performance and relatively low latency. Section Summary. In this section, we explore advanced chunking techniques like small to big and sliding window to enhance retrieval quality by organizing chunk block relationships. By using smaller blocks to match queries and returning larger blocks with contextual information, we demonstrate the effectiveness of these techniques with the LLM embedder model. Additionally, we discuss the importance of selecting the right embedding model, enhancing chunk blocks with metadata, utilizing vector databases for efficient retrieval, and evaluating different retrieval methods to improve performance, with hybrid search and hide being recommended as the optimal approach. Section: Hide with different concatenation of documents and query. In this section, we explored how different ways of combining documents and queries can impact retrieval performance using hide. We found that combining multiple pseudo-documents with the original query can improve retrieval performance, but it may also increase latency. There is a trade-off between retrieval effectiveness and efficiency. Simply adding more hypothetical documents does not necessarily improve results and can significantly slow down the process. Using just one hypothetical document is often enough. We also investigated the effect of varying the weight on sparse retrieval in hybrid search. By adjusting the weighting between sparse and dense retrieval components, we can enhance retrieval effectiveness. After evaluating different weight values, we determined that a weight of 0.3 provides the best performance. This adjustment can improve retrieval effectiveness to a certain extent, so we chose this value for our experiments. Following the initial retrieval phase, we implemented a reranking process to boost the relevance of retrieved documents. This phase reorders documents to ensure the most relevant information appears first. We considered 2 approaches: DLM reranking, which uses deep language models for classification, and tilde reranking, which focuses on query likelihoods. These approaches prioritize either performance or efficiency. DLM reranking involves fine-tuning deep language models to classify document relevancy to a query. On the other hand, tilde reranking calculates the likelihood of each query term independently. We conducted experiments using different models and found that Minot 5 is a well-rounded choice, while Rank LLAMA excels in performance, and tilde 2 is the fastest for fixed collections. To optimize subsequent processes like LLM response generation, we introduced a document repacking module. This module rearranges documents based on their relevancy scores from the reranking phase. We tested 3 repacking methods: forward, reverse, and sides, and selected the sides method as the default option. In the context of summarization, we highlighted the importance of summarizing retrieved documents efficiently to aid LLM response generation. Summarization methods can be extractive or abstractive, and we focused on query-based approaches. We evaluated different methods on benchmark datasets and recommend Recomp for its excellent performance. Long LLM Lingua, although not as effective, shows promise for generalization. Additionally, we explored selective context, a non-query-based method, to compare its effectiveness with query-based approaches. Section Summary. In this section, we explore the impact of different concatenation strategies for hypothetical documents and queries using hide, finding that concatenating multiple pseudo-documents with the original query can significantly boost retrieval performance at the expense of increased latency. We also investigate the influence of different weighting values in hybrid search, revealing that an alpha value of 0.3 yields the best performance, showcasing the importance of adjusting alpha to enhance retrieval effectiveness. Additionally, we delve into reranking methods, where DLM reranking and tilde reranking are compared for their efficiency and performance, with recommendations for Minot 5 as a balanced approach, rank LLAMA for optimal performance, and tilde 2 for quick results on a fixed collection. Section: Generator Fine-Tuning. In this section, we focus on adjusting the generator to improve its performance while leaving the retriever adjustment for later exploration. We want to see how fine-tuning affects the generator, especially when considering relevant or irrelevant information. We use a query denoted as X and contexts denoted as D. The fine-tuning loss of the generator is based on how well it predicts the correct output Y. To study the impact of fine-tuning, we look at relevant context D_gold and randomly retrieved context D_random. We train the model using different context compositions: D_G with relevant documents, D_R with one random document, D_GR with a mix of relevant and random documents, and D_GG with two copies of a relevant document. The generator without fine-tuning is labeled as M_B, and the fine-tuned models under different contexts are labeled as M_G, M_R, M_GR, M_GG. We fine-tuned our model on various QA and reading comprehension datasets, using ground truth coverage as the evaluation metric. We chose Llama 2 to 7B as the base model. After training, we evaluated the models on validation sets with different context compositions and also without retrieval. Our results show that models trained with a mix of relevant and random documents perform best when given either relevant or mixed contexts. This indicates that training with a combination of relevant and random contexts can improve the generator's ability to filter out irrelevant information while effectively using relevant information. Therefore, we recommend augmenting training with a few relevant and randomly selected documents as the best approach. More details on datasets, parameters, and results can be found in the appendix. In the next section, we explore the best practices for implementing RAG. We started with the default practices for each module and iteratively optimized individual modules until we found the most effective options. We fine-tuned the Llama 2 to 7B chat model with a mix of randomly selected and relevant documents for each query as the generator. We built a vector database using Milvus, including 10 million English Wikipedia texts and 4 million medical data texts. We also studied the impact of removing query classification, reranking, and summarization modules to understand their contributions. We conducted extensive experiments across various NLP tasks and datasets to evaluate the performance of RAG systems, including common sense reasoning, fact-checking, open domain QA, multi-hop QA, and medical QA. We assessed the RAG capabilities on subsets of these tasks using metrics like faithfulness, context relevancy, answer correctness, and retrieval similarity. The evaluation metrics varied based on the task, such as accuracy for common sense reasoning, fact-checking, and medical QA, and token-level F1 score and exact match score for open domain QA and multi-hop QA. The final RAG score was calculated by averaging these capabilities across tasks, and we analyzed up to 500 examples from each dataset. Section Summary. In this section, we focus on fine-tuning the generator to explore the impact of relevant and irrelevant contexts on its performance. By training the model with a mix of relevant and random documents, we found that the generator's robustness to irrelevant information improved while effectively utilizing relevant contexts. Augmenting training with a few relevant and randomly selected documents emerged as the best approach for enhancing the generator's performance. Section: Results and Analysis. In this section, we will discuss the key insights derived from the experimental results presented in the table. The query classification module plays a crucial role in enhancing both effectiveness and efficiency, resulting in an average score improvement from 0.428 to 0.443 and a decrease in latency time from 16.41 to 11.58 seconds per query. Regarding the retrieval module, although the hybrid with hide method achieved the highest RAG score of 0.58, it comes at a significant computational cost of 11.71 seconds per query. Therefore, we recommend using the hybrid or original methods to reduce latency while maintaining similar performance levels. The absence of a reranking module led to a noticeable performance drop, emphasizing its importance. Minot 5 showed the highest average score, highlighting its effectiveness in enhancing the relevance of retrieved documents. This underscores the crucial role of reranking in improving response quality. In the repacking module, the reverse configuration demonstrated superior performance with an RAG score of 0.560, indicating that placing more relevant context closer to the query leads to better outcomes. The summarization module showed superior performance with recomp, although removing this module could achieve comparable results with lower latency. However, recomp is preferred due to its ability to address the generator's maximum length constraints. Removing summarization could effectively reduce response time in time-sensitive applications. Each module uniquely contributes to the overall performance of the RAG system. The query classification module enhances accuracy and reduces latency, while the retrieval and reranking modules significantly enhance the system's ability to handle various queries. The repacking and summarization modules further refine the system's output, ensuring high-quality responses for different tasks. Based on our experimental findings, we propose two distinct practices for implementing RAG systems tailored to specific needs, one focusing on maximizing performance and the other on balancing efficiency and efficacy. For the best performance practice, incorporating specific modules and methods yielded the highest average score of 0.483, albeit with higher computational intensity. On the other hand, the balanced efficiency practice recommends a configuration that strikes a balance between performance and efficiency, aiming to reduce latency while maintaining comparable performance levels. We have extended the RAG system to multimodal applications by integrating text-to-image and image-to-text retrieval capabilities. These capabilities offer advantages such as groundedness, efficiency, and maintainability. Retrieval methods provide information from verified multimodal materials, ensuring authenticity and specificity, while also being more efficient compared to generation methods. We plan to expand this strategy to include other modalities like video and speech, exploring efficient cross-modal retrieval techniques.